Okay, so hi everyone, welcome to our Wednesday colloquium. So today is a great pleasure to welcome Dr. Eva Laplace. So let me say a few things about Eva. So Dr. Laplace is originally from Strasbourg, France. She did her undergrad at the University of Tübingen in Germany. She worked on X-ray binaries, observations of B X-ray binaries at ESA during her bachelor in Madrid, and Riken, Japan, for her master's. Wow, that must have been very interesting. So so then she moved back to the flatland, the Netherlands, at the University of Amsterdam, where she studied with the group of Selma de Mink and Steven Jatham. And in 2021, just when she graduated, she received an outreach award from the Royal Holland Society of Sciences and Humanities for the visualization software Tulips, which we all enjoy using very much, I must say. And so now, since 2021, for a year now, she's a postdoc at the Heidelberg Institute for Theoretical Studies in Germany, in the stellar evolution work of Fabian Schneider. So today she's going to talk about binary evolution and massive stars. So Eva, thanks a lot for accepting our invitation. And yeah, the floor is yours.
Thank you. Yeah, thanks a lot for having me. I'm really excited to talk to you today. And today I'd like to talk to you about how binary evolution affects the late evolution, death, and afterlife of massive stars. And I'm going to just start by talking about this new group I'm part of at the Heidelberg Institute for Theoretical Studies. And so this is a group by Fabian Schneider, funded by an ERC grant. And we are growing, as you can see. And I think it's an exciting new start for some new stellar evolution science. Okay, so I work on stellar astrophysics, as probably many of you also do. And I think it's a really exciting time to work in this field because we are really at a moment where we can start to answer very fundamental questions about stellar physics. So for example, how do stars evolve? How do they die? What do they leave behind? And what happens when it's not just one star, but there are multiples that can interact? And it's also really exciting because we have a new window to the universe thanks to these amazing gravitational wave measurements, which give us more insights about compact objects. And just to give you an impression of what this looks like, here we have all the masses of pretty much all compact objects that we knew about before the event of gravitational waves started to be measured on Earth. And what you see here is just a depiction of all the masses that you can find in what they call the stellar graveyard. So you have electromagnetic black holes and electromagnetic neutron stars, and this is the distribution. But our picture has dramatically changed in the last few years. This is how it looks like now. And it's quite amazing when you think about it. So we really have actual good statistics now about compact objects. And that's very, very exciting because it gives us an independent view on the remnants of stars and their properties. So of course, these compact objects come from somewhere. And we have many reasons to believe that most of them come from massive stars. And these massive stars are really, really interesting because they have many properties that are really crucial to explain many things in the universe. So massive stars are these bright blue objects that you see in this picture, and they have very strong stellar winds. They produce elements in their centers up to the iron group, And they are responsible for ejecting these elements in the universe, and these elements are the elements we are made of. So that's quite nice. So for example, the oxygen that we breathe and the carbon that we're made of, it's all produced in the cores of massive stars. And massive stars are also really fun, of course, because they collapse at the end of their lives if they are massive enough. So I'll be really, during this talk, focusing on massive stars that are able to do so. So that is depending on which parameters you assume. These are typically stars that start their lives with masses of about 10 and above solar masses, 10 times more than the mass of our sun. And then when they collapse, two things can happen. In principle, they can explode and produce these beautiful supernovae, or they can collapse and create black holes. And I am going to tell you about this today. But of course, we all know that massive stars have this other very interesting property, and that is that most of them don't live alone, but have a companion. And that means they live close to another star. And actually, we know that massive stars are particularly interesting because they not only have companions, but companions so close to them that they will most likely interact during their lifetime. And today, I'd really like to focus on one particular type of binaries, and these are these binary strip stars. So these are the stars, so on the right side of this picture here. So these are the stars that are initially the more massive stars and that transfer matter to another star. So these are the donors, if you like. And what is really fun about these strip stars and why we study them is that they're really, really common. So if you make some predictions, how many of these stars should interact, you can see that it's really the largest group of stars are going to be the ones that remove their outer envelopes and transfer these to their companions. Also, what is really nice about binary strip stars is that compared to other outcomes of binary evolution, they are easier to model. So they can quite reliably be models with still evolution codes because we can understand quite well what happens at the surface of these stars, which is a bit more tricky for creating stars or mergers. But we also work on that. If you're interested, I can tell you more about this. Also, these binary strip stars are really, really crucial because of the formation of gravitational wave sources. So I started with today. So you can see that when you have two isolated binary stars, so two stars that live together and don't interact with anything else during their lifetime, if you want those two stars to create two black holes that will create emit gravitational waves and be measured on Earth, then they go through several steps during their evolution. And there are many, many steps to discuss here. I think some of you are specialized in some particular steps shown on this diagram, but I just want to highlight two of these today. And these are these steps that happen after these stars interact and transfer matter. And what I want to point out here is that in both cases, for the standard way that we see that two isolated stars can create two black holes, we expect that the progenitors of the supernovae, so the stars that come before the explosion, are both strip stars. They probably look like Fourier stars if they're quite massive. And if they're less massive than that, then it's a little bit more unknown how they look like, but we call these binary strip stars. And so this is a very, very important point. So these stars that will form black holes or that will explode, these are both strip stars in both these phases. Okay, keep this in mind. It's going to be important for later parts of my talk. Okay, So how does this look like when we look at the typical evolution of such a star on the Hertzsprung-Russell diagram, our favorite astrophysics diagram, where we see the luminosity of a star and its effective temperature, which is something like its color, with red on the right side and blue on the left side, and which means cool and hot, respectively. And if you have a single star, this is shown in gray, then you have this very typical track where the star becomes more luminous during its main sequence when it burns hydrogen in its core. Then it expands. After hydrogen burning starts all the subsequent burning phases here, while it is already a red supergiant. So a very, very large star can be something like 500 times the radius of our sun. So this diagram is not always very intuitive. So if we try to show this diagram in a different way, we can show this movie here. So you will see exactly the same evolution, but just have an idea of the scale, what's happening here and how the star changes color. And if I play this movie, you'll see exactly what I was describing. So as the star follows this track that you can still see in this inset here, it changes color, becomes larger and larger and larger and larger. Yeah, and becomes a red supergiant. Okay. And now if I go back to binary evolution, how does that look like? So now let's say we have exactly the same star, something like 10 solar masses, a bit more. And now it has a companion star that is a little bit less massive. What happens? So at the beginning of the evolution, this is shown in purple here, you have exactly the same evolution. The star just gets bigger and brighter. And then it will leave the main sequence, become even larger on a much faster time scale. And then it will be so large that it will fill its Roche lobe and transfer material to its companion star in a stable mass transfer phase. And after that, it will become much hotter and tinier and become what we know as a strip star. And what I'm mainly going to focus on today is the last part of the evolution, when the star actually expands again and then becomes a strip star. So you can see a very, very different outcome here. Yeah, exactly the same star at the beginning, but it had a companion star. And so the outcome of the evolution is extremely different. And also the evolution is quite different. So again, if I show this as a movie, then you see again this evolutionary track on the left corner, and otherwise you see this circle that represents the star and its color. And you can see the star becomes larger and larger and larger. And then it reaches a critical radius where it can transfer mass. And then it becomes tiny. Actually, here I cheated. On this scale, you wouldn't be able to see the star anymore. But I just made it such that you can still see a dot here for the visualization. But just to give you an idea of the scales these stars go through as they get binary stripped. It's quite impressive. Okay, so what have we seen here? Oh yeah, these animations were made with this tulips code. It's an open source Python code that you can use if you like to visualize the evolution of stars. Can do many, many things. If you're interested, just go check it out. And so what we've seen so far is that binary stripping really affects the life and the death of stars, and especially their outer layers. Yeah. But now here is a very interesting question to ask at this point. What happens actually to the core? It's quite clear that if you transfer the material from the outer layers, yeah, that's going to change the surface of the star quite a bit. But it will also affect the core. Yeah, that's a very important question. And so we looked at this a couple of years ago. And what we looked at is the final composition of a star, whether it's a single star or if it's a binary strip star. Is it the same? If you have the same core, not even the same initial mass, but the same core mass, will you have the same structure inside the star if the star is a single star, or if the star is a binary strip star? And of course, you can already guess what the answer is, but I'm just going to explain very briefly what you see here. So what you see here is the helium core of a single star at the end of its life. And all these colors represent different elements inside the star. And as you can see, there are different layers. So there's this helium-rich layer that we call the helium core. Inside this helium core, you have an oxygen, neon, magnesium-rich region. It's typically called the oxygen core. And inside that region, you have a big mix of many, many things that we call iron. It's actually a bit more complicated than that. It's just iron group elements. But just to simplify, this is what we typically refer to as the iron core of the star. And now if we show the same distribution, and by the way, this also has some quantitative information. So actually, as you go, so the surface area here indicates the actual mass of that element inside the star. So here you can see that the iron core is something like half the mass of this core. And now if we compare this to the chemical composition of a binary strip star, we see something really fun. So the basic structure is very similar. You have these regions, the helium-rich region, the oxygen-rich region, and this iron region. But you have some additional layers here. Yeah, there's this pocket of carbon around this oxygen-rich core that is not present in single stars. And if you repeat this for many different models with the same core mass again, you can see that this is actually the case for basically all the masses. And that has some nice consequences. And so the reason why we get these different chemical abundances is that when the star transfers matter during core helium burning, the response of the core is different, and that will lead to different chemical reactions being, so a different nuclear reaction, being dominant. And so you will create, in general, you will leave more carbon behind in these strip stars, and you will not do that in single stars. So this is pretty fun. This means that if you transfer matter away from the surface of a star, if you do this at the right time, during core helium burning, basically, then that will, or before core helium burning, then this will really affect also the deep interior of the star. And this has really fun consequences. So one of the things we've been looking at is what this means for also the ejected material in the life of the star. And we specifically looked at carbon. And carbon is a really fun element because it's the basis of any organic molecule, right? We all made predominantly of carbon. It's also, there was also some debate about the origin of carbon in the universe. Some other stars have been claimed to be able to make carbon. And so we've been looking at what this means if you have this different chemical structure of the star at the moment of explosion, what it means for all this carbon that is going to be ejected. So what we call the yield, how much carbon are you going to make? And there's, of course, the possibility to eject carbon through winds, and it's possible to eject carbon also during the supernova explosion. And what we found is that these binary strip stars are really better at ejecting carbon into the universe. And that is one, because they have strong winds, and two, because they retain this carbon pocket. And it's actually quite difficult when this supernova shock goes through the stellar structure. It's quite difficult for this supernova shock to destroy that region because it's quite far out, as you could see. And by the time the shock reaches this region, it has already cooled down quite a bit, can't really destroy it. And then you can eject more of this carbon. So this was pretty fun. And so my colleague, Rob Farmer, has also been expanding this work to look at many, many different elements, which is also really fun and exciting. And just a key takeaway point I want to give you here is that stars in binary systems, so especially these binary strip stars, produce quite different elements from single stars. And it's really fun to think about. So because this has not been looked at so far. So most of the predictions for stellar yields are based on single stars. And here we really find that there's quite a difference. So what you see here on the x-axis is actually just an idea of the fraction of the ejected material that comes from different sources. So from single stars before they explode, from single stars when they explode, and from binary stars when they explode, and binary stars before they explode. And you can see that there's quite a scatter here. So this means that everything that is above that dashed line here, their binary strip stars are better at ejecting that material. And under this line, it's more single stars. So there's quite some diversity here, and that's something to be explored. Okay, so we have seen that binary stripping also affects stellar yields. Okay, and now I'd like to come to the last part of my talk, and that is another consequence of these different structures. So really trying to explain which stars actually form black holes and what kind of black holes do you expect from single stars, what kind of black holes do you expect from binary strip stars, and does that match up with observations? So I think we've all learned this in Stellar Evolution 101. So which stars become what? So your typical low to average mass star, something like the sun, is expected to become a white dwarf at the end of its life. Then as you increase the mass, we are expecting neutron stars to be formed. And then as you go to even higher masses, we expect mainly black hole formation. Yeah. Well, this picture is wrong. And that's actually quite fun. So when you look at detailed supernova models, and you look at which stars explode and which stars collapse, so which stars will form a neutron star most likely, and which stars will form a black hole. And this is really all in this neutrino-driven mechanism framework. But basically, many, many groups have shown that you expect something like this picture here. So here you have the initial mass of a star on the x-axis, and this is just an idea, give you an idea which star explodes, which star doesn't. Yeah, and you can see it's quite a mess. So it's not like you can say, oh, above 15 solar masses, all stars form black holes. That's absolutely not the case. There is some structure here. Yeah, and this is something we've been looking at, and it's quite exciting. So why is this the case? Why do you have these regions here? And that's not so easy to answer. But one way to look at this in a simple way is to basically look at the stellar structure. You look at the core of a star, and you try to see, okay, how compact is a core at the end of its life? And if it's very compact, then you expect that the star is going to make a black hole. And if it's less compact, then it's going to make a neutron star and explode. And this is something that has been done actually by many, many different people, many different groups. And what is really exciting about this is that everyone seems to find exactly the same patterns. When does this ever happen in stellar evolution? I think this is quite exciting. And And what is actually happening there physically? Why is it that stars with core masses of about 7 solar masses will be more compact than stars that have a larger mass core? Yeah, so we've been looking into this. So this is still work in preparation. But basically what is happening is that there is a transition in the way that nuclear burning happens in the core. So typically this region here corresponds to the time when the nuclear fusion of carbon in the core becomes radiative. And that is because basically the nuclear energy generation rate becomes higher than very, very high neutrino losses that happen in the core at that time. And you will have transition from a convectively burning core to a radiative burning core. And we can actually show that this happens further in this mass regime as well. So here we had it for carbon burning, core carbon burning, but it also happens for core neon burning, and it also happens for core oxygen burning. So it's all these transitions in the nuclear fusion that create, lead to stars being more compact or less compact, but it's something we still need to work out. Anyway, if we take this core compactness as a first proxy for stars that will create black holes or stars that will become neutron stars, we can see some very interesting things. And here I have to remind you that, of course, most stars, as I already told you before, don't live alone, and they will actually interact with a companion. And this really changes their properties at explosion. So what we found is, so I already showed you that the composition is quite different in the core, but we also found quite a different nuclear burning structure. And a different density structure. And that will really, really affect the explosion, as I showed you before with this compactness. So what we see on this figure is a single star. So this half circle represents a single star. And on the right, I compare it to a binary strip star. And they both have exactly the same core mass, but they have very different properties. So they have different burning regions. And these burning regions are not at the same location in the star. And this will mean that they have a different compactness for the same core mass. And this is something that is shown here. So this is something a little bit more advanced than compactness, but it's the same idea. So you have quite some structure in this plot. I will try to walk you through it. So these dark blue dots, I'm sorry, I forgot the legend. These are single stars. This is, and we can see what the mass of the compact object that produces. And in this light blue color, basically you have these strip stars, and there is some other binary strip stars at different times in red and in yellow, and these correspond to case A and case C. For those who are interested, but that's not the point. So the point is, you have quite a different structure here in the stars that will form black holes and the stars that will form neutron stars. So if you have the same initial mass, stars that live in single stars will form black holes for lower initial masses. And stars that are stripped in binary systems will form them for higher initial masses. So actually for binary strip stars, it's really difficult to make black holes. Yeah, you need a star that starts off either with more than 70 solar masses, yeah, so very, very rare, or a star that starts off with something like 35 solar masses. And then you expect what we call this compactness peak, where you will form black holes. So keeping this in mind, I hope this was clear. Please just feel free to ask if if you need more explanations. So I just want to point out the black holes here, but you can also see, of course, very interesting structures in the neutron stars that you expect. Yeah, so there is a much wider range of possible initial masses for creating neutron stars from binary strip stars than from single stars. And the properties of these neutron stars are also different. Yeah. Okay. So why is this important? Again, I want to come back to this picture of this isolated binary evolution. If we play this game and ask, okay, you have two stars here and you want to form black holes. You want to form two black holes at the end that can merge and create gravitational waves. And now we use this quantity, we use this compactness to predict which stars are going to make black holes. Remember, both of the stars that will create black holes are not single stars, but they are binary strip stars. Yeah. So if I come back to this picture, this means that these stars will create black holes for different initial masses than single stars. Yeah. So if we play this game and we try to predict, okay, so what would you expect in general as a mass distribution from these stars? If we pair two stars together that will make black holes, where would they be? And what we find is that you can create black holes here when you have two stars, two black holes that are formed in this first peak I was talking about. You can form black holes here for a much larger range for black holes that were formed from this other region where you have more possibilities to create black holes at high initial masses. And you can pair them together, and then they will form black holes with these chirp masses. So these basically a combined weighted mass of these stars that will lie in this region. And it turns out, I'm not going to show it to you here, but I hope but we can discuss that it's actually quite difficult to pair up black holes from this first peak and from this peak. From binary evolution theory, it's quite difficult to pair them together because it's only possible for very specific masses. And this means that we predict a gap here. Yeah. Okay. So if we compare this to the chirp mass distribution of detected black holes so far, this is the outcome. And so what we see seems to match quite well with the observed distribution of LIGO, Virgo, Cagra black holes. Yeah, so what you see, so what I'm showing here is, so it's more arbitrary units, to be honest. So these are basically the chirp masses, and with their errors shown here as Gaussians, plotted for each individual event. And on top of that, you have this cumulative distribution of all these events. So just looking at this, it's quite interesting to see, right? We typically think about these cumulative distributions and not the individual events. It's quite interesting to see that there's a gap here, yeah? And that seems to be quite in line with what we expect from just pairing up stars that will make black holes at these specific compactness peak. Yeah. So this is quite exciting, and it's a paper currently under review. Yeah, I'd be very happy to discuss this with you further. But I think I'm already at the end of my time. So I will go to my conclusions. So what I've tried to show you here in this talk is that binary stripping not only affects the outer layers of stars, but it really affects also the deep interiors, which means that it affects the core structure of stars. So whether they will make black holes or neutron stars, but also the chemical structure of stars, and with that, the elements that they're able to eject. So supernova nuclear synthesis. And also stars that evolve in these isolated binary systems produce black hole masses that are quite different from single stars. And our predictions of disturbed mass distributions from isolated binary evolution seems to agree with gravitational wave observations, which is pretty fun to think about. Okay, so that's it. Thank you very much.
So Eva, thank you very much for this very exciting talk. I will clap for everyone. So are there any questions for our speaker? Please just speak up. I have many questions, so but I will just give people the opportunity to. Okay, Andreas has a question. I see. Andrea, go ahead.
Yeah, thank you, Eva. Sorry, I missed the first part of your talk because I was in another meeting. But I have a question regarding the final conclusion about the mass gap. Does this apply only on the gravitational wave events, or okay? Because I was wondering, we do know that there are X-ray binaries with black holes in this range. So
yeah, very good point. Yeah, actually, what I haven't told you yet is that the next step is to compare predictions to the mass distribution of black holes and X-ray binaries. Yeah, so that's a very good point. So I think something to keep in mind is that the masses determined for X-ray binaries are affected by very large systematics, as you probably know much better than me. For example, the mass of Cygnus X1 has doubled, right, in the past years, and now people seem to agree that it has 20 solar masses, which was actually, by the way, agree very well with our predictions from this theory. But yes, this is a very good point. So another point is, I talked about predictions from isolated binary evolution. And so this means really two stars that will not interact with anything else. But of course, in the whole spectrum of things that we see around us, we don't only expect this channel to produce black holes. So it is actually quite possible that there are other channels, like for example, in clusters, where you could expect stars of actually any mass to, not any mass, but of a wider range of masses for black holes. So this is one point. And the other point is, yes, from isolated binary evolution, this is actually quite suppressed to create black holes in this gap. But we do expect some black holes to be able to do this. And this also shifts if black holes are able to accrete mass. So, you know, it's this is all, we do expect that it will fill up at some point, probably. But it should not, so from our expectation is that it will not be completely filled up, which already, by the way, tells us something about the most likely channels, right? If we are right within this theory, who knows? But if this is correct, because this is also, I mean, based on neutrino-driven explosions, who knows if stars really explode like this? But if this is correct, then this means that if this, so with the new events and all of this, if you keep having a mass gap here, then this probably means that isolated binary evolution produces a lot of the black holes that we see, which is also really fun.
And also a related question, do you have predictions for the fraction between black holes and neutron stars in binary systems? Because that's another observational test, both in terms of gravitational wave events, but also from X-ray binaries.
Yeah, that's a very good point. So far, we have not done any population synthesis predictions. This is, we're hoping that people get excited about this and do that for us, to be honest. So here, these are not population synthesis calculations. These are really purely expectations from the stellar evolution models. Where would we expect masses of black holes?
Okay, so these are runs for individual systems.
Yes.
Okay.
Yeah. So this is not. So we do expect that the population will be something like this. So the distribution will probably be in these ranges that are indicated by these boxes. It's quite unlikely that it will be outside of this. And with the height here, we try to indicate how large the contributions are expected to be. But to really fully answer this question, we need population synthesis, and this will be done by other people.
absolutely, yeah. Okay, thank you.
Thanks.
Thank you, Andrea. Any other questions? So maybe I can ask a couple of questions.
Yeah, sure.
So just to so that's obviously like a third mass gap. It's not the usual mass gap people.
No. Yeah. People typically think of this mass gap here. Yeah.
So I was wondering.
I'm talking about this.
Well, just so first of all, is it possible to say a few more things about your progenitor models? I mean, how were they calculated? How far along?
Absolutely.
And then also, how do you calculate the compactness parameter, or if you use something else?
Yeah, that's a very good point. Yeah, so maybe no, this is not something where you will see it. Yeah, I think I have the model somewhere in my backup slides because I was expecting. Yeah, so maybe this is a way to see these models. So this is actually, these models were already published. So these were in the Schneider paper. So these are so there are single stars, there are binary strip stars. And so these are MESA calculations, and we use very canonical parameters for everything that you would think would influence the explosion outcome. So we use some typical step overshooting above the hydrogen burning core and the helium burning core. And we use our carbon alpha rate that corresponds to the default MESA, I think the Kunz rate, if I'm not mistaken. And maybe something else that could affect this is the wind mass loss, of course. And this is also something that we have more details about this. There's this region of LBV mass loss where we're not really sure what the outcome is going to be. So this is indicated here between these gray bars. There we think that our predictions are probably not very correct, but we do assume that these stars, most of them will make black holes. So these models are actually already published. And now to come to how we evaluate which stars will explode and which one will not. This was used by using actually an explosion code from Bernhard Müller. So that was published in 2016, in his 2016 paper. And it's a calibration to 3D neutrino-driven explosions, and where you can take the entire stellar structure into account to predict the explosion outcome. And we have cross-checked with compactness, with the Ertl parameters, with other explosion parameters that we find quite similar explosion outcomes for these structures. But yeah, yet again, of course, stellar evolution will shift these peaks left and right, depending on some uncertainties, and probably the biggest uncertainties are the carbon alpha rate, the overshooting. There are some metallicity effects as well, but and we even discussed this in this paper, but I didn't want to make it too complicated. And the other thing is of course wind mass loss, but that affects mainly the higher mass range, so it will not really affect the prediction of this mass gap that we really focused on. Yeah, so I hope it's a bit more clear, but I didn't want to put all these details here.
Very, very clear. So
okay, great.
Thanks a lot. And then I guess I was wondering, what is can you make any predictions about the lower mass gap? So the low mass, the lower mass
neutron stars
gap between neutron stars and black holes.
Yeah, that's a very good point. Yeah, and I think here we have, of course, as you might expect, we have this problem of the fallback. Here I didn't talk about fallback. Yeah, but it is possible that some of the, so actually quite expected for some mass ranges, for some stellar structures, it is expected that the star is not going to be able to explode to disrupt. So the shock is not going to be able to disrupt the star completely, but there will be some material falling back, and actually so much that you will collapse again into a black hole. And this is something here. So you see these gray boxes here. these are stars where we expect that actually they will most likely form black holes if you take fallback into account. And the reason I'm pointing them out is that we expect that these stars, if they have this fallback, they will maybe accrete half of their envelope or something. But just accreting this amount of material will put them immediately in this mass gap between neutron stars and black holes. So we have predictions about this. Actually, we have some fun things about black hole neutron stars as well. This is just the beginning. We have to explore all of this. There are many, many more predictions about this. So there, for the neutron star range, it's also really fun, right? Look at this.
Absolutely.
This spread. Yep. It's quite fun that you have quite a spread in mass for these neutron stars coming from binary strip stars compared to neutron stars coming from single stars. And this is something that should be observationally testable. And the good news is that anyway, the best constrained masses for neutron stars come from binaries. So we do expect that they will follow this trend. So this is something we need to explore, and it's definitely the next step in this study. It's just the beginning. So I will look mainly at X-ray binaries and black holes in X-ray binaries, but we definitely plan to also have a look more on neutron stars. Yeah, that's a very good point.
Absolutely, yeah. I mean, David has also been testing Bernhard's code.
Oh, great!
His models, and
Mm-hmm.
actually Bernhard has a new version of his model where he also takes into account this partial fallback in the supernova.
Oh, great! Oh, yeah. Mm-hmm.
And some of this, I mean, one thing that he finds is that some of these actually do fall in this mass gap. So yeah,
I'm not surprised. I'm not surprised. I think it's quite easy, actually. You only need to accrete quite a small fraction of the envelope to fall into this mass gap. So it's we do expect, if fallback is a thing, yeah, this is also something that we will learn about with more data. Then we do expect that you will fill this mass gap between neutron stars and black holes quite easily. Yeah. But if it doesn't happen in nature, that is also really fun, because that makes all our predictions much more robust, to be honest. So yeah, this remains to be seen. But I would like to point out something here, and that is that we predict actually quite a narrow range here of masses. Depends a bit on how much the black holes accrete, and that's other details like this. But you can see there is already, in the few observations that we have, there's already quite a spread. Yeah. So how do you produce this spread in masses? Could be from different overshooting for different stars, but it could also be from fallback. You can also shift this distribution with fallback. So maybe this is already a sign of this. And also you can already see outliers, yeah? So we cannot produce them with this channel. So this can tell you something about formation channels. But yeah, so that there's a lot of information to be extracted from this work. Yeah, but I think there's quite a number of these topics have already been discussed a little bit in the Schneider 2021 paper. Yeah. So yeah, there's a start for some discussions on, for example, neutron star distribution there. But yeah, there's much more to be done. Yeah.
I agree. Yeah, thank you, Eva. So I see Manos's hand is raised. So Mano, go ahead.
Yeah. Hi, Eva. It's great to see you again. And
yeah, nice to see you too.
Thank you for this very interesting talk. It was enlightening in many points. So my question would be about the supernova prescription that exists in the market, and to focus mostly on there are the works of Patton et al., where they argue that they can predict in a way the outcome of the explosion based not only on the core mass but also on the core abundance.
Yeah, that's a very important point. Yes,
yes.
Absolutely.
So my question would be, what do you think that a prescription that doesn't only have the core mass but has also the core carbon abundance, but still 2 parameters to try to say something about the explosion, would it be enough to capture at least qualitatively most of the complexities that you have been discussing in all of your talk, or is it still a too simplified prescription?
No, so that's a very, very good point. So I didn't go too much into explaining the compactness and why we see this these trends in compactness. But you're absolutely right that the main quantities that determine the compactness are the abundance of carbon in the core at the end of core helium burning and the CO core mass. And we've been looking at merger models a little bit, and there we see that actually the helium core mass also plays a very second or third order role there. But as a first order approximation, just using the core carbon abundance and the CO core mass is an extremely good proxy for the explosion. It's the main thing that determines the compactness. So you can absolutely use this, and it's going to be probably much better than anything that is out there in the population synthesis so far, because it takes into account really the core structure of stars. So I think this is absolutely something that I hope some people will pick up now that Theodor Zuckbold has left academia. So I hope someone does that. But we are working on this, actually. We are looking into this, and I'm currently looking into really explaining these compactness peaks with a bit more clearly with really what is happening in the core when there are these different properties. And this, of course, depends, as I mentioned before, on the uncertain rate of carbon alpha captures and core overshooting, all these things. But this also gives us an opportunity, right? Because if we do see such clear features in the future, right? If this remains correct, we don't know. But if this is really the picture, then it will actually help us constrain these quantities. This will help us constrain the carbon alpha rate. And we have other independent measurements of black hole formation that can help us do that.
Right, so thank you, Manos. And are there any final question for our speaker? Right, so if not, we can end the seminar here. So Eva, thank you very much again.
Yeah, thank you so much for the invitation.
And so bye everyone, and see you next week. Bye.
Bye bye.